Welcome back to the channel. If you've been following the saga of interstellar object 3I Atlas, you know that for months the scientific community has been holding its breath. We thought we had a handle on this visitor. We thought we understood its trajectory, its composition, and its behavior as it swung through our solar system. But new data has just come in from the Hubble Space Telescope, and to put it bluntly, everything we thought we knew might need to be rewritten. Let's look closer at the data. On December 12th and again on December 27th, 2025, Hubble turned its Wide Field Camera 3, specifically the UVIS channel, using the F350LP filter toward 3I Atlas. These weren't quick snapshots. These were deep 170-second exposures at a wavelength of 0.58501 microns, designed to capture the faintest details of the object as it begins its long journey back out into the dark. What the astronomers expected to see was a fading comet, perhaps still venting a little gas as it moved away from the sun. What they actually found has reignited a firestorm of debate in astrophysics departments around the globe. The images reveal a structure that shouldn't be there. Instead of a simple dying coma, 3I Atlas is displaying a dramatic, unexpected double jet structure. This is not a subtle feature. The data shows a dominant sunward jet, a massive stream of material blasting toward our star, which is forming a long, distinct anti-tail. But that's not all. Accompanying this primary feature is a second, weaker jet pointing in the exact opposite direction. It is a bilateral eruption that defies the simple models we built just a few months ago. Before we dive deeper into the physics of this anomaly, if you want to stay on the cutting edge of space exploration and get these deep dives as soon as the data drops, make sure you hit that subscribe button and turn on notifications. We are tracking this story in real time, and you won't want to miss the updates coming in the next few weeks. Now, why is this double jet so shocking? To understand the surprise, we have to rewind the clock to July 21st, 2025. That was our last major benchmark observation. Back then, Hubble looked at the same object and saw something completely different. In July, there was only a single, elongated jet. It was a focused beam of material, roughly 10 times longer than it was wide, streaming off the object. At that time, the geometry seemed clean. It seemed understandable. We were looking at a classic cometary behavior, albeit from an interstellar source. This finding sharply contrasts with the July 21st, 2025 Hubble observation. In that dataset, the single jet was the defining feature. It was consistent with a specific active region on the surface of the object being heated by the sun. But now, 5 months later, the script has flipped. We aren't just seeing a change in intensity. We are seeing a fundamental change in morphology. The emergence of a second jet, pointing in the opposite direction, suggests that something profound has happened to the internal or surface dynamics of 3I Atlas in the time since it passed its closest point to the Sun. The December images are painting a picture of a body that is far more complex than a simple chunk of ice and rock tumbling through the void. The dominant jet is creating an anti-tail that stretches toward the Sun, a phenomenon often seen in comets when heavy dust particles are left behind in the object's orbit. However, the presence of the counterjet, the weaker stream firing away from the Sun, complicates the picture. This contradicts what we previously thought about the object's rotation and active zones. If this were a simple comet, we would expect the activity to diminish as it moves away from the heat of the Sun. Instead, we are seeing the activation of new regions, or perhaps a complex interaction between the object's rotation and its thermal inertia. The December 12th and December 27th observations are not just static pictures, they are snapshots of a dynamic, evolving process. The wavelength data is critical here. Observing at 0.58851 microns allows us to see reflected sunlight off dust and gas. The fact that these structures are visible at this specific wavelength tells us about the material being ejected. We are looking at physical matter, dust, gas, ice, being accelerated away from the nucleus. But the symmetry, or rather, the asymmetry of these two jets is the puzzle piece that doesn't quite fit. Why would a comet moving away from the Sun suddenly decide to fire its thrusters, metaphorically speaking, in two opposite directions? The dominant sunward jet is behaving somewhat predictably, forming that anti-tail. But the weaker jet, the one pointing away, that is the anomaly. It implies that there is an active region on the night side of the object, or perhaps that the object's rotation has exposed a previously dormant face to the vacuum of space in a way that triggers outgassing. We have to consider the timing. These images were taken post-perihelion. 3I Atlas has already survived its closest encounter with our star. It has been baked, pulled by gravity, and bombarded by solar radiation. The structure we see now is the result of that trauma. The single jet from July was the prologue. This double jet structure is the main event. The resolution of the WFC3 UVIS camera is incredible, but even it has limits. We are looking at pixels that represent thousands of kilometers of space. The jets appear as streaks of light, brightness variations against the background of stars. But by analyzing the intensity profiles of these streaks, astronomers can model the density and velocity of the material. And the models are struggling to keep up with the reality. The anti-tail is particularly fascinating. In cometary science, an anti-tail often appears as a spike projecting toward the Sun, caused by larger dust particles that aren't pushed away as easily by solar radiation pressure. They stay in the object's orbital plane. The fact that 3I Atlas has such a prominent anti-tail suggests it is shedding significant mass, large grains of dust that are lingering in its wake. But then you have that second jet. Is it a counterflow? Is it a separate vent? Or is it a trick of perspective? The 170-second exposures rule out transient noise. This structure is real. It persisted from December 12th to December 27th, though as we will discuss later, its brightness shifted. This persistence confirms that we are witnessing a sustained release of material, a continuous burn, if you will, that is altering the object's appearance on a massive scale. The scientific community is currently scrambling to run simulations that can explain this geometry. How do you get two jets of unequal strength firing in opposite directions on an object that is retreating from the heat source? Standard cometary models usually predict jets on the sunlit side. To have a jet on the opposite side requires a mechanism to transport heat through the body of the object, or a source of internal pressure that we haven't accounted for. This is the mystery of the double jet. It is not just a curiosity, it is a challenge to our understanding of interstellar physics. It forces us to ask whether 3I Atlas is made of the same stuff as our local comets, or if its composition is fundamentally different, allowing it to retain heat or volatile pressure in ways we don't see in our own solar system's inhabitants. As we stare at these grainy, high-contrast images from Hubble, we are seeing the silhouette of a traveler that refuses to be categorized. The single spear of light from July has transformed into a double-bladed structure, a cosmic signal that the story of 3I Atlas is far from over. The data is clear, but the interpretation is murky. And in that murkiness lies the excitement of discovery. So, what does this actually mean for the trajectory and the nature of the object? To understand that, we have to look at how 3I Atlas has been moving, how it spins, and how its dance with the sun has altered its orientation in space. Because the jets aren't just pretty streamers, they are evidence of forces that are pushing and pulling this object as it flies. We need to look at the orbital dynamics. We need to understand the wobble. And that is exactly what we are going to do next. The double jet is the what, but the how involves a complex interplay of gravity, rotation, and momentum that we are only just beginning to unravel. As we established in the previous chapter, the visual appearance of 3I Atlas has undergone a radical transformation. The emergence of a double jet structure in the December Hubble images has thrown a wrench into our initial models. But to truly understand why these jets are appearing where they are, we have to stop looking at the object as a static picture and start looking at it as a dynamic, moving body in three-dimensional space. We have to talk about orbital dynamics, rotation, and the chaotic dance this visitor has performed with our sun. Building on this, let's revisit that single jet from July. Remember, back then, the jet was a singular focused feature, 10 times longer than it was wide. It was a needle in the haystack of the cosmos, but even then, it wasn't perfectly steady. Careful analysis of the July data revealed that this jet was wobbling. It wasn't a straight line, it was tracing a cone in the sky. Specifically, that earlier jet was found to wobble by about 7 degrees around the rotation axis of 3I Atlas. This wobble is a smoking gun. It tells us that the object is spinning, and more importantly, it tells us about the orientation of that spin. The wobble suggested that the jet originated near the pole of the object that was facing the sun. Imagine a spinning top. If you paint a dot near the top of the stem as it spins, that dot stays relatively stable, just wobbling slightly. That was the situation in July. The North Pole of 3I Atlas, if we can call it that, was pointed roughly toward the sun, baking in the heat and spewing out material in a tight column. But then came October. On October 29, 2025, 3I Atlas reached perihelion, its closest approach to the sun. This is the moment of maximum stress for any comet or interstellar object. It is the point of maximum heat and maximum gravitational pull. As it whipped around the sun, 3I Atlas experienced a gravitational deflection of 16 degrees. That might not sound like a U-turn, but in celestial mechanics, a 16-degree shift in trajectory is significant. It's a hard bank turn at hypersonic speeds. Here is the crucial detail. This gravitational encounter didn't just bend the path of the object, it likely altered our viewing geometry and the object's orientation relative to the Sun. Think about the geometry. Before perihelion, the object was approaching the Sun, and its north pole was illuminated. But as it curved around the star and began its outbound journey, the angle of the Sun changed. The pole that once faced the Sun, the one that was generating that single strong jet in July, may now lie on the night side of the object. It has rotated into the shadows. This geometric flip provides a compelling framework for understanding the new double jet structure. Intriguingly, this orientation aligns with the weaker of the two newly captured jets. The theory is that the old jet, the one from the pole that was active in July, is still firing, but it is now pointing away from the Sun into the darkness. It has become the weaker, secondary jet we see in the December images. It's like a dying engine, still sputtering, but no longer receiving the direct solar energy that fueled its peak activity. Meanwhile, a new region of the object has rotated into the sunlight. The south pole, or whatever region is now facing the star, has been exposed to the full brunt of solar radiation. This fresh surface, previously frozen in the dark, is now sublimating violently. This explains the stronger jet now rising from the opposite side, facing the Sun as 3I Atlas escapes back into interstellar space. So, the double jet might not be two simultaneous eruptions from a stable body, but rather a transitional phase. We are witnessing a changing of the guard between active regions. The old active zone is fading as it rotates into night, and a new active zone is waking up as it rotates into day. This connects to the broader question of the object's shape and spin state. If 3I Atlas were a perfect sphere, this transition might be smooth, but the wobble of 7 degrees suggests it is elongated, perhaps cigar-shaped or pancake-shaped, similar to Oumuamua, a non-spherical body tumbling through space, subject to the uneven heating of the Sun, experiences torque. The outgassing itself acts like a rocket thruster. If the jets are not perfectly aligned with the center of mass, they push the object, causing its spin to accelerate or decelerate. The fact that the July jet was 10 times longer than it was wide implies a high velocity of ejection and a very specific, narrow nozzle or active area. Now, with the December data showing a dominant sunward jet forming a long anti-tail, we are seeing a different kind of flow. The anti-tail suggests larger particles, perhaps dust grains, that are being pushed back by radiation pressure but are heavy enough to lag behind. This is a messy, broad release of material, contrasting with the tight beam we saw earlier. The geometry is the key to unlocking this mystery. We have a body that has been torqued by gravity and reshaped by heat. The 16-degree deflection was the turn. The appearance of the second jet is the reaction. We are watching 3I Atlas pivot. It is presenting a new face to us, and that face is reacting explosively. But this orbital dance raises more questions than it answers. If the weaker jet is just the old active region rotating into the dark, why is it still active at all? In the cold vacuum of space, cut off from sunlight, why wouldn't it shut down immediately? And why is the new sunward jet so much stronger? Is it just because it's in the Sun? Or is the material on this side of the object different? This brings us to the physics of the jets themselves. We have the wear and the when, the orbital mechanics, and the orientation. Now we need to understand the what. What are these jets made of? How can a comet sustain activity on its night side? And could there be a more exotic explanation for this dual exhaust configuration? Scientists propose two possible explanations for the appearance of the dual jets. One is grounded in the natural physics of comets, heat conduction, volatile ices, and dust dynamics. The other, the other takes us into the realm of the unprecedented. To understand if this is a natural phenomenon or something else, we have to look at the particles. We have to look at the heat. We have to look at the physics of the jets. Given what we now understand about the orbital gymnastics of 3I Atlas, the wobble, the deflection, and the shifting pole, we are left with a physical puzzle. We have a mechanism for why the jets are pointing where they are, but we still need to explain the mechanism of the jets themselves. How does a frozen rock in space generate two distinct streams of matter with such different properties? Scientists propose two possible explanations for the appearance of the dual jets. Both are grounded in physics, but they paint very different pictures of what 3I Atlas is actually made of. The first possibility is the thermal lag or heat conduction scenario. This theory suggests that the jets are indeed launching from opposite sides of the nucleus, driven by the thermal history of the object. Imagine a brick of ice and rock. As it swings past the sun at perihelion, one side gets blasted with heat. That heat doesn't just vanish when the object rotates, it soaks in. It conducts through the body of the comet. In a natural comet scenario, heat absorbed near perihelion could have conducted through the body, reaching pockets of volatile materials like frozen nitrogen, carbon monoxide, or water ice, buried deep beneath the surface or on the far side. This trapped heat could be activating these volatiles on the night side, causing them to sublimate and burst out into the vacuum. This would produce the weak jet we see pointing away from the sun. It's a ghost jet, powered by the memory of heat absorbed weeks ago. Meanwhile, the day side, currently baking in direct sunlight, remains more responsive and emits a stronger, more immediate jet. This explanation is elegant because it fits with what we know about cometary physics. We've seen thermal lag on comets like 67P, Churyumov-Gerasimenko. But 3I Atlas is showing a stark contrast, a strong primary jet and a weak secondary one. The difference in intensity suggests that the night side activity is struggling, perhaps choked by the cooling crust, while the day side is free-flowing. But there is a second hypothesis, and this one is even more intricate. This hypothesis suggests that both jets might actually originate from the sun-facing side, but they look different because they are made of different stuff. So, what does this actually mean? It means we might be seeing a sorting mechanism in space, driven by the pressure of sunlight itself. In this scenario, the jets are actually a single stream of debris that is being separated by solar radiation pressure. Imagine throwing a handful of sand and feathers into a strong wind. The sand, heavy, flies forward, while the feathers, light, are blown back. The theory posits that dust grains roughly 10 microns in size, relatively heavy and chunky in cosmic terms, could sustain the massive anti-tail. These particles are too heavy to be easily pushed around by the pressure of sunlight. They follow the object's orbit, trailing behind it and forming that long, sunward-pointing structure stretching hundreds of millions of kilometers. On the other hand, gas, submicron dust, or slowly ejected particles behave like the feathers. They have a high surface area to mass ratio. As soon as they leave the surface, the photons from the sun slam into them. They experience strong radiative deceleration. They are literally pushed backward by the light. If they are ejected slowly enough, they might quickly turn around and flow past the object, forming the counterjet pointing away from the sun. This particle sorting theory explains the visual data without requiring complex internal heat tunnels. It explains why the anti-tail, heavy dust, looks different from the counterjet, light gas, dark dust. It's a beautiful demonstration of physics in action, gravity versus radiation pressure. But how do we know which theory is right? We can't fly a probe there to check, but we can use light. In this scenario, upcoming spectroscopic studies, potentially conducted by the James Webb Space Telescope, JWST, could be the tiebreaker. JWST can analyze the jet velocity profiles. If the heat conduction theory is true, the night-side jet should have a velocity consistent with ejection from the surface. But if the particle sorting theory is true, the counterjet should show signs of deceleration and reversal. We would see the material slowing down and then accelerating away from the sun. Specifically, scientists will be looking to determine whether the weaker jet accelerates outward with increasing distance. If it does, it supports the idea that radiation pressure is driving it. If it maintains a constant velocity or dissipates, it might be a vent. This is where I want to hear from you. Which of these natural explanations sounds more plausible to you? Is 3I Atlas a porous sponge soaking up heat and venting it out the back? Or is it a dusty snowball being sifted by the solar wind? Drop your thoughts in the comments below. I read through them after every deep dive, and some of your theories on the last video were spot on. These natural explanations are robust. They fit the standard model. They use known physics to explain a strange observation. But there is a lingering what if. There is a subset of the data that makes some researchers pause. The anti-tail appears marginally opaque. The velocity requirements for the particle sorting theory are tight, and the sheer symmetry of the jets is suspicious. What if the jets aren't a reaction to heat? What if they aren't a passive cloud of dust? What if they are functional? A more speculative interpretation suggests that 3I Atlas could be something else entirely. Something that isn't just tumbling through space, but navigating it. It's a hypothesis that sits on the fringe, but in the face of such anomalous data, it demands to be examined. In the next chapter, we are going to take off the natural comet hat and put on the techno-signature hat. We are going to look at the possibility that 3I Atlas is a technological construct and how these jets might serve as a defense mechanism or a propulsion system. As we established, the natural explanations for 3I Atlas, thermal lag and particle sorting, are scientifically sound. They rely on the known behaviors of ice, dust, and sunlight. But science is also about testing the boundaries of the possible. And when an object exhibits behavior that pushes the limits of our standard models, we are obligated to ask the outlier questions. We are obligated to consider the technological hypothesis. A more speculative interpretation suggests that 3I Atlas could be a technological construct. This is not a claim we make lightly, and it is certainly not a confirmed fact. But let's perform a thought experiment. If this object were artificial, how would we interpret the double jet structure? In this scenario, the jets stop being passive plumes of gas and start looking like active systems. Consider the environment 3I Atlas is traversing. It has just grazed the sun. It is moving through a region of space filled with intense solar radiation, solar wind, and the potential for coronal mass ejections, CMEs. For a delicate interstellar probe, this is a hostile zone. Could the sunward jet be a defensive measure? If 3I Atlas is a probe, the dominant jet facing the sun could be a plasma shield or a physical barrier. By ejecting a stream of material toward the star, the object creates a bow shock, a buffer zone that deflects the high-energy particles of the solar wind around the main body. This would protect sensitive instruments or the structural integrity of the craft from the searing heat and radiation. This idea gains a sliver of traction when we look at the optical properties of the jet. The data indicates that the anti-tail appears marginally opaque. In a natural comet, the tail is usually diffuse and translucent. An opaque tail suggests a high density of material, perhaps a specific type of particulate matter, designed to absorb or scatter light and radiation effectively. It acts like a smokescreen, a physical shield deployed to mitigate the solar assault. But what about the second jet, the weaker one pointing away from the sun? In a technological context, a secondary jet could provide protection or navigation against potential hazards in the object's outbound trajectory. As the object leaves the solar system, it is moving into the wake of the solar wind. A rear-facing jet could clear debris, stabilize the object's orientation, or even provide a small amount of thrust to adjust its course. If this were a propulsion system, we would expect to see specific kinematic signatures. If 3I Atlas were technological in origin, both jets would be expected to launch near the nucleus at speeds exceeding 1 kilometer per second. This is a high velocity, much faster than the typical lazy drift of cometary dust. A speed of over 1 kilometer per second implies a high-pressure ejection, a nozzle, a mechanism that accelerates the material with intent. This is where the particle sorting theory we discussed earlier faces a challenge. If the jets are just dust blowing in the wind, their velocities should be relatively low near the source. If they are thrusters or shields, they should be fast. The upcoming JWST data will be the judge. If we see high-velocity spectral lines originating right at the nucleus for both jets, the natural particle sorting theory takes a hit, and the technological needle moves slightly, just slightly, out of the red. We must also consider the wobble in this new light. A natural object wobbles because of uneven mass loss and torque. A technological object might wobble because it is scanning, or perhaps the wobble is a side effect of a damaged stabilization system. The 16-hour period, the 7-degree tilt, are these random numbers or are they operational parameters? It is crucial to remain skeptical. Extraordinary claims require extraordinary evidence. Currently, we have an anomaly, not a spaceship. The double jet can be explained by physics without invoking aliens. But the shield hypothesis offers a functional logic to the geometry that is hard to ignore completely. It explains why you would fire a jet, at where the danger, the sun, and why you might need a stabilizer in the back. The technological hypothesis also reframes the changing brightness of the jets. If these are engineered systems, the variations in brightness might not just be rotation, they could be modulation. They could be the throttling up and down of an engine or a shield generator in response to the changing solar environment. This brings us to the most striking feature of the December data, something that bridges the gap between the natural and the artificial interpretations. The jets didn't just appear, they changed. Between December 12th and December 27th, the object didn't just sit there, it evolved. The brightness shifted, the shape morphed. Whether it's a melting comet or a malfunctioning probe, 3I Atlas is alive with activity, and the rhythm of that activity, the heartbeat of the object, is the final clue we need to examine. In the final chapter, we will look at this heartbeat, we will look at the future, and we will ask the ultimate question: what happens next? We have looked at the images, we have analyzed the orbits, we have debated the physics of dust versus the speculation of technology. But the story of 3I Atlas is not a static one. It is a story of change. And the most striking feature of the December data is how different the jets appear across the two observation dates. Between December 12th and December 27, 2025, the object didn't just drift, it transformed. Their brightness and apparent shape changed markedly between these two windows. This isn't just a trick of the light. It is a behavior that may reflect rotational wobble if the jets are misaligned relative to the object's spin axis. Imagine a lighthouse beam sweeping across the ocean. As the light rotates, it brightens and dims from your perspective. 3I Atlas seems to be doing something similar. The data shows a rhythmic exchange of energy. The anti-tail brightens while the opposite jet dims and then reverses. It's a cosmic seesaw. One side flares up, the other fades, and then they switch. This rhythm is reminiscent of the heartbeat brightness variations measured in July 2025. Back then, astronomers detected a periodic dimming and brightening that followed a roughly 16-hour period. That was the pulse of the object, the rate at which it was spinning. The fact that we are seeing a similar, albeit more complex pattern in the jets 5 months later confirms that rotation is the engine driving this display. But there is a twist. Similar to theories proposed for 1I Oumuamua, the first interstellar visitor we detected, mass loss may have altered the rotation rate of 3I Atlas since mid-year. When a comet ejects gas, it's like a skater throwing a heavy weight. The recoil changes their spin. If 3I Atlas has been venting material for months, its 16-hour day might have shortened or lengthened. It might be tumbling more chaotically now. New Hubble data will be used to test this possibility. Astronomers are currently stitching together the light curves from December to see if that 16-hour heartbeat has skipped a beat. If the rotation period has changed, it will allow us to calculate exactly how much mass the object has lost, a crucial number for determining its density and composition. So, what is next? The immediate future belongs to the James Webb Space Telescope. While Hubble gives us the visible light structure, JWST will give us the chemistry. It will peer into the infrared, cutting through the dust to see the thermal signature of the nucleus itself. It will measure the velocity of the jets. It will tell us if there is water, carbon monoxide, or organic molecules. The December observations of 3I Atlas underscore how rapidly assumptions can collapse under the weight of new evidence. In July, we thought we had a simple, wobbling comet. By December, we had a double-jet anomaly that defied easy explanation. Whether this interstellar visitor is a natural relic, a shard of a destroyed planet, a wandering iceberg, or something engineered, the evolving behavior seen in its strange jets serves as a reminder. It reminds us that the universe still holds secrets that refuse to fit into familiar narratives. We want to put things in boxes: comet, asteroid, spaceship. But 3I Atlas sits in the space between those boxes. It challenges us to look harder. It challenges us to refine our models. And most importantly, it challenges us to keep watching. The object is leaving us. Every day it gets fainter, smaller, and more distant. But the data we are gathering now will be analyzed for decades. If you enjoyed this deep dive into the unknown, and if you want to support content that prioritizes scientific curiosity over easy answers, please hit that like button. It helps the algorithm find other curious minds like yours. The search for answers requires not certainty, but curiosity. 3I Atlas is fading into the dark, but the questions it left behind are burning brighter than ever. Thanks for watching, and keep looking up.